So here we are, projectile motion, and we're through some of the stuff that we need to know about vectors, and we want to start using them. So we're going to look at motion in 2 dimensions, and a great way to look at motion in 2 dimensions is to talk about projectile motion, because it's something that you've probably seen before, especially in an introductory physics class, and so it'll give us a way of being able to use what we've learned and really kind of at the same time, we're going to rehash projectile motion so that we're comfortable with it, so that we remember it. And then also maybe try and insert a little bit of I hat and J hat notation so that we can start using that. So, motion in 2 dimensions, of course, doesn't have to be just projectile motion. It can be tons of different things. But we're going to start with projectile motion and go from there. So, remember, draw a diagram of the situation if necessary. Obey sign conventions that we set up with our Cartesian coordinate system. Very often it'll be helpful to place the origin where the motion starts. And we want to take any initial velocity and resolve it into x and y components. So, let's start and let's look at an example. A golf ball is launched from a rooftop with a velocity of 20 meters per second at an angle of 30 degrees above the horizontal, from 45 meters above the ground. Find the time of flight and the horizontal displacement. And let's begin. So here's our little diagram of our golfer on top of a roof. We put 0 where the motion begins, so that's at the rooftop. The ground then would be at negative 45. And we know that V1 is 20 meters at 30 degrees, so we can draw our little diagram. And we can have V1x and V1y. And if we resolve it, V1 can then be 20 cos 30 I hat plus 20 sine 30 j hat. Our displacement in the y direction is minus 45 j hat. Our acceleration is in y, so it's minus 9.8 j hat. Our range in x we don't know. And our time we don't know. So let's put these things together. We're going to start with displacement equals v1t plus 1/2 at squared. And so we can write this now using our I hat, J hat notations. So some range x in I hat minus 45 j hat, that's our change in displacement, equals 17.3 I hat plus 10 j hat. If you're wondering where I got those numbers from, look up to V1. 20 cos 30, 17.3. 20 sine 30 is 10. Minus, of course, 1/2 at squared is minus 4.9 j hat t squared. So here we are. We want to keep our x's, we want to keep our I hats together, and we want to keep our j hats together. So let's write now 2 completely separate equations that comes from this 1. And that's what we're going to do. So here we have our equation that we got from j hat. Minus 45 is equal to 10t minus 4.9t squared. And we've got x is equal to 17.3t. So now we're back on track. Now we're very, very familiar with what we should be doing. You've probably seen this before. We can't solve for x or for t from the equation on the left because there's too many variables. But we can solve for time from the equation on the right. So let's rearrange this. This, of course, is a quadratic equation. And we can solve this quadratic equation. And we get 2 roots. One of them is inadmissible. So we take this guy 4.22 seconds. So that's how long the projectile is in the air. We can now use this result in our equation up top. We can say, okay, 17.3 times 4.22, and we get 73 meters. So that's kind of a very, very simple, straightforward first example. Here's example 2. A Yukon rescue plane drops a package of emergency rations to a stranded party of explorers. If the plane's traveling horizontally at 40 meters per second and is 100 meters above the ground, where does the package strike the ground relative to where it was released? So, of course, the package that's dropped is a projectile because it has some initial velocity. So here's a little diagram of the situation. We've got a plane traveling 40 meters per second, and the dotted path represents the path that the package would take, not the path that the plane would take. So what do we have? V1 is equal to 40 I hat meters per second. We know that the acceleration is minus 9.8 j hat meters per second squared, because acceleration in this case is straight down. And our displacement vector is some distance x in the I hat direction minus 100 in the j hat direction, because it's falling 100 meters. So again, we can put this together. D equals v1t plus 1/2 at squared. And we can write x I hat minus 100 j hat equals 40 I hat t minus 4.9 j hat t squared. Separating out our equation for the I hats and our equation for the j hats, we have minus 100 j hat equals minus 4.9 j hat t squared. At this point, we can do away with the j hat because we're talking about being in the exact same direction. We can get rid of it. We get 100 over 4.9 is equal to t squared, and we can solve for time. So the time that the package is in the air is 4.5 seconds. Over here, in the x direction, we've got x I hat equals 40 I hat t. Again, now we can just do away with the I hats. We don't need to worry about them. And we've got x is equal to 40 times the time the package is in the air, 4.5 seconds. And we can solve for 180 meters. So the package lands 180 meters down from where it was released in the x direction. So try this. This is a good little example for you to try. Find the velocity of the package just before it hits the ground. So just as it hits the ground, what's the velocity of the package? So try that. And to challenge yourself, try and work in your I hat and j hat notations. Okay, the answer is 40 I hat minus 44 j hat meters per second. Okay, so try it and figure it out. Second question, once you've done that, is try this. Where is the plane located when the package hits the ground? And that one, well, we'll just wait. We'll just leave the answer for now.